Okay, all welcome to Mets Connect Tech Talk, Flying on Water. It's no surprise that we're talking about contemporary foilers with that title. Hydrofoiling technology has been around for more than a century, but recent developments in materials and ride control technology have pulled them into the mainstream of sailboat racing with the America's Cup and Vendée Globe, and more consumer-oriented foiling in recreational powerboats. But before we get to the current high end, let's start with some of the basics and a firm grounding in the research of foil geometry from our friends at the Maritime Research Institute of the Netherlands. Luigi, I'm going to call on you. Talk about some of the areas of hydrodynamic research in foils that you've been exploring most recently.
Thanks, Aaron. Yes, I think that in the past years we have been at MARIN busy to, let's say, re-explore this technology, and I'm sharing some of my screen to give you the idea. Basically, what we have done is indeed, as you rightfully summarized, new applications reinitiated the interest in something that was learned already news in the 70s, in the 60s, the 50s, even before. And now that thanks to material and power computing, we have witnessed the new possibilities. We have to take also into account what do we need to do to face the challenges that this type of technology has. And some of them have is the takeoff, the flying stability, the influence of some specific hydrodynamic phenomena like cavitation and ventilation. So at MARIN, we have considered typically what are the operational objectives of these concepts and link them to the topics of research and find for these topics of research at the hydrofoil craft level, what are the best, what are the investigation methods that are required. And we have basically we have two types. We can do experimental experiments, physical experiments, or numerical. And the choice of each of them depends on what is your objective, which hydrofoil key factors you are interested into, and or craft factors. So I give you a very quick example because I don't want to take too much time. But for example, here, this is in experiments where you can study the wall hydrofoil craft on the bottom, especially putting attention on the dynamic control in full foiling mode or the takeoff. In other case, you are more interested to the dynamics to study the dynamics of the foil in when cavitation and ventilation are occurring, or even include in these experiments the hydroelastic behavior of the foil. How is the forming when all of these dynamic phenomena are occurring? One thing I was showing is the possible investigation methods that we have to deal with the wall hydrofoil craft, like on the bottom when you want to investigate a full foiling craft with the dynamically controlled wings, or investigate the takeoff, which is another aspect of interest in these applications. But sometimes you need to zoom in to the behavior of the foil in isolated, first of all, in isolated condition, to really grasp the dynamic characteristics of the foil. And there is an example in what I'm sharing on the top left of my slide, where this foil is actually tested alone with incavitating condition by applying some force oscillations. This is an example when you want to investigate experimentally. Another, as a second but complementary step, is when you can do also this type of investigations numerically. And all of these tools and methods have been and are currently used to look at the key factors at craft level or at hydrofoil level, because for different purposes. I go back to what I was showing at the beginning. This is actually the first overview that initially was not probably shared, is that in hydrofoil crafts, you have certain operational objectives: safety, comfort, performance, efficiency, and those are complex, in a complex way linked to different key factors at craft level and at the same time at hydrofoil level. As a research institute, what we are doing is actually in some cases trying to find the right investigation method to deal with the key factors at hydrofoil craft level, and sometimes you need to look at the hydrofoil level. The nice and challenging aspect of hydrofoil design is that all of these aspects are strictly interconnected. So you can't, if you really want to have a successful design or a successful assistance in that, most of the time you need to take into account not only the hydrodynamic behavior of the foil, but also its hydroelastic behavior. How is the forming due to the hydrodynamic loads? Because this has an impact on the performance itself. This is an example to show how intimately linked are these elements. But again, the right tools for the right specific topic. So the reason I was showing these videos was to say sometimes you need to look at only the single foil to gather the dynamic characteristics which can be used then for the dynamic control of the vessel, as it is explained in the picture in the videos below, or to explore the hydrostructural behavior. All of these aspects are linked. We have performed actually 3 model test campaigns in the past 3 years about 3 different topics. Actually, one was in 2018 was related to the dynamic control of a full foiling craft. In 2019, we zoomed in to understand better the dynamic behavior of the single foil when phenomena like cavitation, which can be responsible of a sudden loss of lift of almost 1/3, which can imagine in terms of safety has a huge impact, for example. Or even this year, recently, we, in collaboration with the Michigan and Iowa University, we have studied the link between the deformation of the foil and the occurrence of these unsteady phenomena like cavitation and ventilation. The reason of these studies was, first of all, to understand what do we need to do to perform these studies, what kind of equipment we require, and what kind of data. For example, and I can also conclude with that example, when we talk about deformations of the foil, I think you are still seeing my screen exactly. An example, we could instrument an hydrofoil with some sensing beam that could measure the deformation of the foil and couple it with the developed forces of the foil itself. So here, for example, you could see the moment when a foil is about to ventilate. So the red signal is the lift. And when all of a sudden you have ventilation triggered, there is any sudden loss of lift. And that's an aspect that has an impact not only on the performance of the foil, but also in terms of capability to lift and let you fly faster and cleaner, but also on the safety itself. And how to predict this behavior is one of the other challenges in this experimental setup. So with this, I wanted to give you a bit of an overview of the type of studies that are possible, depending on the objectives of the research itself, stressing the exquisite aspect that the hydrofoil design has really this very strictly coupling of so many phenomena that to assist properly the design needs to be treated sometimes separately, but then put together the pieces of the puzzle in order to give a successful design.
Fabulous, thank you. Annie, we've got time for a quick question if there's one from the other participants here. Anything that Mark or Lionel want to weigh in on or ask of Luigi?
Yes, perhaps I can ask one question to Luigi. Do you make a calculation with a composite foil or a metallic foil?
It is in our research plan the possibility to study composite material foils. We are actually, for example, busy in studying experimentally and numerically the properties of propellers with in composite material. And the propeller blade is like a wing, a foil. So we are definitely making the steps in that direction, because they are a necessary coupling.
Yeah.
Super, thank you. Great. We'll move on to our next segment, where we'll explore the material side of the equation a little more. Lionel, you're a composite supplier, Certex. Tell us about some of the considerations that must go into the material selection for these really highly loaded appendages, and what material properties you as a provider of laminate material are looking to optimize for foil builders. Thanks.
Yes, thanks Aaron for sharing, and thanks to Luigi for his presentation. If I can resume, you talk about design, you talk about stress, a lot of stress. We need something light, we need something strong. So for me, we talk about composite mainly. And what we can see on the market today is that foils are mainly in composite today. So I can share my screen to show you some things we've done in the past, in the past. Is it okay for the sharing?
Yep, we see it fine. Thank you.
Okay, perfect. Thank you. Certex, as you know, is one of the reinforcement provider of the world. I would pass rapidly, not to take two times, about another vision concerning foils and marine. For us, it's also sustainability, because you want to have less consumption with foils. You want to go faster, but we have to take care about our resources also. So this is always in our vision in Certex. I pass the company presentation. We are worldwide, of course, and this is really the heart of our technology and what we propose today. I would say we want to give to all customers the right fiber in the right place. This is really hard to define, especially for foil, which type of fiber you need and where do you have to place it. So this is really what we do in Certex today. We can work in many directions. We have machine for that with a specific droppability technique application. We can do also hybrid for people if you need, for example, more carbon in the 0 degrees of the product, or more glass or aramide or whatever. And this is why Certex is interesting today on the market, because we can use all the fiber we want in our machine. We make studies actually with flax fiber, with basalt fiber. This is really a new move in the marine industry and in foil industry today. This is just for explaining Certex today. We develop a lot of tailor-made products and also services to people, because each boat need a special foil, I would say, because it depends on many things, of the weight, of the weight, on the power, on the width of the boat and whatever. So we have to develop and to take care about engineer demand in each case. I would say not only for foils, but for all the structure, of course. We can push in many things. We have a lab for that. We can propose to all people, all our technician guys and technician lab. We've got all certificates because we work also in aeronautic, aerospace, in wind industry and automotive. So everything is really used today and focus on customer needs and customer demand and technical aspect for that. You can see after that for people, I will show you just later on. We develop, especially for foil application, a really high level of cutting proposal to the customers. You will see, I will show you immediately. The first big example I can show now is about this boat, the Candela boat. I think everybody knows this boat today. Candela wants to promote a new vision like a Tesla for cars. They said they need the Candela of the sea, and as you can see on the right back the picture, we developed with them all the carbon structure of the boat because they decided to go to carbon. So we talk about material, we talk about a lighter boat, fast sport boat, who needs a lot of rigid structure and a very light structure, and very light foil also that we can see on the photo. So carbon here is really the main task with them, and we develop special carbon for them and special product for them. Second example we can give is the last Beneteau Figaro 3 boat. We develop with engineer from Multiplast the orange foil you can see on the photos, and this is for them that we push our kit services to the higher level we never had, because they really want to add specific fiber in specific direction with a special width, and it was a very long work, but at the end this boat is really very performant. Another example we can give is about sea bubble. Everybody knows sea bubble. We were with decision on the first prototype and the 5 first sea bubble, and we develop specific glass fiber for this example. And they choose glass because you cannot use every time the carbon product due to the price. It depends on the market you want to focus. If you choose the 2 first boats like Candela and Beneteau, this was for performance boats and very high qualitative boats and race boats. For sea bubble, it's another philosophy. They want to make the taxi of the sea, as I said. So they choose definitively glass fiber just to have a better price for production. Independent after that, I would say we develop also other mass production products. like this huge boat you can see. I think everybody sees this boat in every trade show today. It's a 100% electric boat, full in sustainability. They really need to be very light due to the battery pack and the weight of the battery pack of this boat. And we developed with them during more than 2 years, very specific product. And at the end, they build today, they start to build the number 5 or 6 of this boat, of this model. What we can say again, to resume, is that Certex is not a foil specialist. Certex is not a marine specialist, but Certex is really the good partner for reinforcement. And we can develop discussion and partnership with people just to find a way to place the right fiber at the right place to get the better value you need in mechanic. So feel free to ask us, and feel free to tell us what is your idea and how can we reinforce your idea. This is the main topic today. And
super. Thank you, Lionel. Any questions from the rest of the panel here?
One question is.
Oh yeah, go ahead.
One question is how do when you decide to reinforce something, to place the fibers in the proper way, you get an input in terms of loads from an external party, or you compute those loads by yourself?
What we have in Certex, we have the knowledge of the resistance of the fiber and of the layup and the direction of the fiber you can put. But at the end, we cannot tell to customers for this boat, for your model, you need to put that just to obtain that, because it's a boat definition first. So we have always to discuss with an architect or an engineer. It gives us a list of the needs for the mechanic or whatever. And after that, we can compare to our knowledge and what we have, and we can compare these data. And at the end, we can find a way. And we propose solution always in a sustainability orientation, as I said first. And at the end, we always search solution to go deeper and faster in production. If we talk about mass production boats, of course.
Yeah, that's good.
Super, thank you. And did I understand, Lionel, you're doing kitting, and that would be true for the foil materials as well? Those will be sort of specified and cut specifically to shape before they're sent on for a production build?
Yes, today in Certex, we can easily participate to all the design in composite parts for people, because we have a lot of machine for kitting. And we can kit all the layup one after another for the customer, and then we deliver a package. So the customer just takes the fiber and put it in the mold, this piece number 1, piece number 2, piece number 3, and at the end, he can have the whole design he wants first.
Great, thank you. Thank you, Lionel. That's wonderful. I think we'll move on as time requires. Wrap up, we'll dive into the deep end of sort of high performance, high stakes foil design and construction. And Mark, your company, Persico, is building all the foils, as I understand it, for the current AC-75s. Can you walk us through the design and development process briefly, if that's possible, for these appendages that will really be asked to perform at fairly close to the edges of their mechanical capacities?
Yeah, thanks, Aaron. Yeah, we'll try and keep it short, eh? Could be here all day. But yeah, talking about the foil arms, I do have a little photo here that I can show. So I thought I'd share this one because it's I quite like it myself, really. It's it looks, you know, you sort of see everything else that you don't normally see on the boat. You know, today they're all painted and you kind of see what's sticking out the outside. And ultimately, I think it's quite good for everyone to see what the raw thing looks like in its real flesh, as I call it. And this is basically what we provide to all the America's Cup teams. I think we've made about 18 of these things so far. You know, this was developed between us and Luna Rosa at the real onset of this project for the AC-75s. And in actual fact, it was developed when there was very little known about the boats themselves, even the loads and the capabilities of the boats. You know, there hadn't really been a mule or there hadn't been anything like that. So everything was done, you know, through computer calculations as such and developed. And then so forth as the project developed, pure engineering in New Zealand was brought in at the later stage, which took us into the second phase of the engineering for the arm. You know, it was a bit of a contributional effort from a lot of the teams themselves and some big players, especially in the Grand Prix market. So I thought it was interesting to at least show this picture. You can see the head on the top. All of the big metal fittings that you can see are all made out of titanium and machined. You know, there's a kind of, you know, the best material used in exactly the right places to perform its right properties. At the bottom end, you can actually see right down the bottom there is where everyone gets to attach their wings. So, you know, for the people that don't know, this is the one design component, and everyone gets exactly the same. And then from the leading edge, this part here down, everyone actually attaches their wings and their own designs and so forth onto the arm. From this point up, it's all the same. This is the lower belt, which essentially is the hinge point of the arms, which rotate up and down. So I thought that was kind of interesting to have a look at. We actually start out, you know, to give people a good idea of how it starts. We actually start out with a number of big plates like this. So we, at the real onset, we had to develop how we were going to build this arm. And this was obviously, it's a 400 kilo arm piece of composite. And what we didn't want to do was to come up with a process that entails us, you know, building a huge, big composite structure, carbon fiber structure, and going through like one process, whether it being a cure or whatever it is, and then finding out that it's actually going to work or not. We needed to have a system in place and a process put in place that guarantees repeatability, so they're all the same. And also make sure that, you know, with composite structures today, it's very, very difficult to build a composite structure that doesn't have any imperfections at all in it. So we ended up doing it in this way. So in every single phase, we could ultrasound it and do a lot of non-destructive testings from the beginning all the way to the end through every phase to build the foil. That in turn wasn't easy. That in turn sometimes wasn't necessarily the fastest approach, but it gave us full repeatability to make sure all the foil arms are the same. And it meant that when we actually get to the end, we know exactly, you know, where we started, if there's any little imperfections or not, whether acceptable or not, all the way through from the beginning to the end. So what we actually had here is we have about 15 or 16 plates like this, which we machine out of very large plates. Then in some of them you can see there's holes. So these are actually lightning holes, believe it or not, to try to make the thing lighter. This saved around about 25 kilos of overall weight out of the foil arm, which, you know, it doesn't seem like much, but in the America's Cup world and the high performance world, 25 kilos is a hell of a lot of weight. So this was then done, and then these things are actually put together and bonded together in a very specific process that is specific to what we do anyway at Persico. A little bit of intellectual property there. And then after that, we machine the foils to the final shape on the outside before they're wrapped. And I think I do actually have a photo here, which I can show you, which is prior to wrapping, which sort of shows you the level of detail that's required. In here somewhere. I don't want to take too much time, but there was a really nice picture in here somewhere. If I can find it. You can actually see it here actually. You know, all of the external surfaces of the foil arm are actually machined. And you know, even for a builder and to do this, it's not the most easiest thing in the world. And it means that to do it efficiently and have control over the process from the beginning to the end, it means you must have a lot of these machinery and infrastructure in place to be able to do it. It's very difficult to be able, you know, to send it out. Even the recesses here that you can see for the fiber optics and cabling that all of the teams get, even that's a one design thing. So, you know, not every, you know, you can't make a bigger hole for your fiber optics to try and, let's say, cheat and make it lighter. You get the same slot as everyone else, yeah, which is quite good. You can see that this is the length of the fiber optic cable also coming from the bottom all the way to the top, and then it actually goes through a small hole in the titanium lower belt fitting to get to the top, and then connects to the team's electronic system themselves. So a couple of extra pictures of the titanium heads. You can see there's a lot of machining out of that head just to take out material where you don't need it, just to make it lighter. And you know, here's a good example of actually what it looks like when it's put inside the yacht. Just so happens my example is the boat that we made, and you can see that, you know, at this approach here, it's difficult to actually understand the connection between one and the other. But there, you know, there is a socket type connection at the bottom there for the wing itself, and based on the roll, the roll actually has a weight, and I think it's about 1.1 tons that the wing on the bottom actually must weigh, and obviously that's for the stability of the yacht. Essentially, when you put the two together at the bottom underneath the boat, they work like two keels and keeping the boat upright, and all the boys and the girls on the inside from falling out of the yacht. And so to maintain that weight, everyone obviously builds their wings to that weight. And if you want to have finer winglets, like you can see on this particular example, then people are putting bulbs in the middle, and generally those bulbs, to make them as small as possible, are generally made out of lead, something that's very heavy, to keep them small as well. What else can I show you? Yeah, there's another example of the two there. You can see the winglets, you know, over time, over the last 12 months, from everybody have been getting, you know, lighter and lighter, smaller and smaller, more and more refined. There's a nice example of how we worked pretty closely with all the engineers, and, you know, the end of the manufacturing of the first foil arm, and we had two test foil arms actually, which in Persico here we have a test bed which is capable of taking the foil arm at 400 kilos, and even other big foils for like Alums, for the big foiling trimarans as such. And we load it into the test bed here, and we actually pull it in every direction you could possibly think of. You can see a lot of cables and things coming off it. It's full of fiber optic cables, acoustic emission control, so we actually have cables positioned all over it. So we have another device which you can see on the right, and we're actually listening and detecting for audible noises, which has some quite sophisticated technology which has been brought through from the aeronautical industry over the years, and we can actually determine where exactly in the foil there's some micro cracking and things like that happening with inside the fibers. It's quite an interesting technology. So we load the foil on the test bed, we slowly bring it up at different levels. We're checking the loads on the foil and the strains within inside the composite structure. as well as how much it's actually deflecting and bending, which is quite interesting. And we do this in all the different load cases until we decide we've learnt enough, and we continue actually pulling it until we break it. And there is quite an interesting video on YouTube. If you go to the Persico site, you can have a look. It's quite spectacular, and it's not very often ever actually, even in my career, that you actually have such a piece of structure, something that costs so much and weighs so much, that you can actually pull it to destruction and learn so much from it. It's absolutely phenomenal.
Mark, thanks. I'm gonna jump in. I have watched that video, and just to warn everyone, there will be a big bang, and you'll jump out of your seat when you watch that. Thanks. I think we're closing in on our end of time here, but I did, one of the things that strikes me with this project is, to a degree, with the one design you're building, you sort of define this as intricately and specifically as possible, design it to be as repeatable as possible, but then the actual designers have to some degree design around the material properties of your appendage. Is that an accurate characterization of the relationship?
Yeah, I think I think that goes without saying for all of the foils that we're involved in over the many years now. And it doesn't matter if it's a small SL33 or AC72 or all the Amoccas these days. Fundamentally, the naval architect or the person that's coming up with the hydrodynamic shapes for the foil themselves and the correct profile, obviously we want to have that as small as possible, so there's less drag, but you want to have it so it gives the right lift, and in doing that you have to basically pack it with carbon fiber. So you need to use intermediate and high modulus carbon fiber, which costs a lot of money, but you can't use too much high modulus because then it actually becomes too fragile actually. So you have to come up with the correct combination and pack the foil with the right modulus fibers in the right place. Then you have to actually put them in the right place, which is a bit like what Lionel was saying. Make sure you got the correct carbon in the right place, in the right direction, so it's loading correctly. And in doing that, you must make sure that the porosity levels are extremely low, if not there is no porosity in it, because these days, because you're packing it in there and you're making the shape as refined as possible, the engineers, they're not taking or wanting to accept too many or too much safety margin. So the safety margins are made smaller, the shapes are more efficient, smaller. We pack it with as much carbon as we can with the least amount of imperfections whatsoever. And it's a very, very difficult task that we all have to work together on and work together between manufacturers, designers, and engineers.
Super, thanks. We're probably over time now, but are there any questions from the rest of the panel? I think we could probably shoot more in one in here. Okay, I think we're fine. That's probably expedient. Thank you all. This has been great, and I hope we'll see you for some questions, live questions after the recording's played here on the 10th.